Hello everybody, and welcome to exercise 1 on page 110 of the workbook. And in this problem, we're going to talk about a little bit of Rapid City, South Dakota culture. So that was the city that I went to college in way long ago. I have to make a little sales pitch for Rapid City before we dive in. So it is a beautiful city right at the foot of the Black Hills. And so if you like hiking, seeing things like Mount Rushmore, check it out. It is a great summer destination. Okay, so let's read what this question is asking us here. So statistics from a popular all-you-can-eat restaurant in Rapid City indicate that 5% of the Rapid City residents who eat there one week will eat there the next week, and that 2% of the residents that don't eat there one week will eat there the next week. Okay, so this is describing a typical stochastic process where we've got the population of Rapid City kind of transitioning in and out of two different states. Okay, so we can maybe start by giving names, okay, to the number of people in each state here. So how about if we call XN the thousands of people who eat at the restaurant in week N? Okay, we'll work in thousands just because that'll make the numbers a little bit more convenient. Okay, so eat at the restaurant in week N. Okay, and then YN will be the thousands who don't. In week N. All right, and so the stochastic matrix is just going to describe the process by which the segments of the population transition in and out of these states that we're talking about. Okay, so why don't we think of going from this week to the next week. Okay, so we'll put this week here, break that into categories of people who eat there or don't eat there. Okay, and then we'll do the same thing for the next week. Here's our two categories of eating there or not eating there. Okay, and we'll call our stochastic matrix that we're trying to figure out P, and then we'll see what the numbers are that are transitioning us between the categories. Okay, so looking back up at the statement of the problem, first number that maybe catches our attention is this 5%. That's the percentage of the residents who eat there one week and also eat there the next week. So that would put a 0.05 for 5%, going from the eat category back into the eat category. Okay, and that means then that the other 95% of those who eat there one week don't eat there the next week. Okay, and then we read a little bit farther in the statement of our problem and we come to this 2%. That describes the residents that don't eat there one week but do eat there the next week. That's going to put a 0.02 up here, and then the other 98% must be down here, going from the no-eat category and staying in the no-eat category the next week. Okay, so there's our stochastic matrix. That gets the process started here, and we are ready to move on to part B then. All right, so they tell us, suppose that 5,000 of the local population of 40,000 eat at the restaurant on a given week. How many will eat there at the restaurant 1 week later? Okay, we can use our transition matrix to answer this question. Okay, so let's start with the numbers that they're giving us. Okay, so think of 5,000 as being an initial amount of people who eat there. So we are given that. X naught equals 5. Remember, we're working in thousands. Okay, and since the total population is 40,000, that must mean that the other 35,000 don't eat at the restaurant. Okay, initially. So Y naught is going to be 35 then. Okay, and so we're interested in knowing what happens after 1 week. So that relates to the quantities X1 and Y1. And we can get those by taking our stochastic matrix, this transition matrix, and just multiplying by, okay, let me just copy it down first, the initial vector. Okay, so the 5 and the 35, X naught and Y naught. Okay, and you can double check me on this, but if you do that matrix multiplication, you are going to come up with 0.95 on the top and 39.05 on the bottom. Okay, now what is that telling us? Okay, those numbers that we just found. Well, remember that the number up above is about the number of people who do eat at the restaurant. The number down here is the people who don't eat there. So we're actually interested in those who do eat, that 0.95. And remember that that's in thousands of people. So we're talking about 0.95 thousand people, or 950 people. All right, so we conclude that 1 week later, about 950 950 residents will eat at this restaurant. Okay, so we have done parts A and B. Let's see if we can do part C now. Okay, so let's see what that's asking us. In the long run, how many will eat at the restaurant in 1 week? Okay, so this is a question about long-run behavior. All right, so if you gave this problem an attempt, you might have approached this the same way that we did the previous example. Okay, you could have diagonalized the transition matrix, taken the limit as n goes to infinity, and found the answer to this question. That's a totally perfectly okay way to do this problem. Turns out, though, that there's a shorter way in this case. Since all we're interested in is the long-run behavior here, what we're really looking for is the steady state vector. Okay, and we described this, I think, on the previous page. So that is the vector Q such that PQ equals Q. Okay, that's what's going to happen in the long run. Okay, so one way to approach this is just to try to solve that equation directly. That's a little bit shorter than diagonalizing the matrix. Okay, so note that if we start with that PQ equals Q, we can subtract the vector q to the other side of the equation. We get pq minus q equals the 0 vector, or we can rewrite it like this. P minus I times q equals the 0 vector. Okay, you might remember the same notation we used when we were talking about eigenvalues. If you're wondering where that identity matrix came from, if you distribute through, you get, on the left-hand side, you get pq minus iq. That's just pq minus q. Okay, and the reason for writing it this way is it gives us a matrix equation that we can solve. Okay, P minus I is our coefficient matrix, and we're trying to determine the value of the vector Q here. Okay, so if we wrote down this equation in system form, our matrix is going to look like P minus I. Okay, so that's just saying we're gonna go back up to our matrix P, which is up here, and we're going to subtract 1 from the main diagonal elements. Okay, so 0.05, the entry in the very upper left-hand corner, 0.05 minus 1 is going to give us a minus 0.95 up there. Okay, and continuing, then we're going to take the 0.98 and subtract a 1 from that as well. That's going to give us a minus 0.02. And over on the right-hand side of our equation is the 0 vector. Okay, so we've got zeros there. Okay, if we can solve that system, we're going to get the value of q, the steady state vector that we're looking for. Okay, so we'll do some row operations here. Okay, and first thing we might do to make the numbers look a little nicer is to multiply through by 100, just to get rid of those decimals. So minus 0.95 turns into minus 95, and we get a 2 here. And notice that if we add the first and the second row, we get a row of zeros down here. Okay, so you might notice that there's a free variable in this system. We've got one pivot position. That's right here with that minus 95. And free variable looks to be x2. So how about if we let that be t? And then if we go back to our first equation up here, substitute in t for x2 and solve it for x1. Okay, I'll leave it to you to double check my algebra. What you should end up with is 2 over 95t. Okay, that's just plugging in t for x2 and solving for x1. All right, so the solution to this system then is, let's write it down. Q equals, okay, and so let's see, in the first position we've got our 2/95 t. And in the second position we've just got a t. Okay, interestingly, this is going to be a solution for any t because t is a free variable. Okay, but here's the thing. We know what the population of Rapid City is. They told us that in this problem. They told us that the population of Rapid City is 40,000. That means that for this to make sense, these two numbers that I'm circling have to add up to 40,000 because those are the two categories. People either eat at this restaurant or they don't eat at this restaurant. Okay, so those two numbers have to add up to be 40,000. All right, so what we know then is that 2/95 t plus t is equal to 40. Okay, that gives us a way to actually determine what the value of t is here. And over on the left-hand side, if you do the addition, 2/95 t plus t, that's going to work out to 97/95 t is 40. Okay, and then one more calculation, just kind of getting that fraction over to the right-hand side. I'll let you confirm my arithmetic. We wind up with 39.175 for our t value. Okay, and now we have enough information to figure out what q is. Okay, so we'll go ahead and substitute that value of q that we got back in. And that's going to give us, let's see, 2/95 times the t that we just found, 39.175, and then down here just the t. All right, and again, you can check my arithmetic. We're going to get a 0.825 up here, and down below we're going to stay 39.175. Okay, now which part of this calculation are we interested in? Okay, well, we kind of scroll back up and peek. They want to know how many people will eat at this restaurant in 1 week. Okay, well, the first part of our matrix, that's the part that's talking about the people who do eat at this restaurant. And so it would be 0.825 thousand, or if we convert just to hundreds, we're going to get 825 people. Okay, so 825 people eat at the restaurant in the long run. Okay, and I guess we should add during a week. That was kind of part of the way the problem was phrased. Okay, and I believe we have completed this question.